Hello. For the Choose Your Own Adventure lab, I chose to do my lab on the falling slinky video. The purpose of this lab was to measure and predict the motion of a stretched out slinky being dropped from rest to determine if and why the bottom of the slinky stays motionless. The physics principles. This lab is based on Newton's second law. I specifically used the velocity update formula in my computational model. The net force acting on the bottom of the slinky is due to the gravitational weight force, drag force, and the tension force from the slinky. Here are the equations for each component of the force. The drag force is the proportionality constant times the square of the velocity. The drag force acts in the opposite direction to the motion, so it is negative. The slinky force is equal and opposite to the gravitational weight force, which is the mass of the slinky times g, acceleration due to gravity. Here is a breakdown of the force body diagrams to better show what is happening with the motion. The top of the spring only interacts with the earth, so there's only a weight force acting on it. Initially, the bottom of the spring experiences the weight force pulling it down, and the tension force from the slinky exerts an upward force. These opposing forces cause the bottom of the slinky to be motionless until the top of the slinky comes down. Then the diagram looks like this. The slinky force is now gone, but there's a drag force acting on the slinky, which opposes the weight force. Here is a video from Tracker of the observed motion. I used Tracker to create a position time graph of the observed motion. I used the average height of the man on the left to estimate the height of the man on the left, to provide a basis for the changes in position for the data. Here's my code. For the beginning of my code, I specified the system properties and the initial conditions. For the mass, I used the average mass of the slinky which I found online. I found the initial position from my tracker data, and the initial velocity is 0 because the slinky is released from rest. I input the g constant and j hat, and I also found the proportionality constant for the drag force and specified it here. For the first while loop of my code, I found the time when the bottom of the slinky began to move and used that time in the while statement. Based on the physics principles I discussed earlier, I wrote the lines for the weight force, slinky force, and the net force. While the bottom of the spring is stationary, the net force is equal to the sum of the weight and slinky force. I applied the momentum principle in the next two lines with the velocity and position update formulas. For the second while loop, which runs while t is less than 9.52, which is when the observed motion ended, the bottom of the spring is now moving, so it experiences the same weight force, the slinky force is gone, and a drag force is now present. I also used the velocity and position update formulas in this loop. Here are my graphs. From my code, I was able to create a computational model for the theoretical conditions based on physics principles. This is shown by the orange line in the graph. The blue line is from the tracker data. The predicted motion is relatively similar to the observed motion with a few discrepancies here and here. The differences could be due to experimental error. From the video, there was slight oscillation of the slinky in the x direction, which was not accounted for in my model. Also, it was difficult to accurately determine the changes in position due to the low resolution of the video, so that could create error in the data I collected for the graph. Thank you for watching.